Good morning, students. Myself, Dr. Pooja Yadav, and we are studying. Just a moment. I'll share my screen and then we will start. Okay. Very good morning to you all. Myself, Dr. Pooja Yadav, and we were studying operational amplifiers and its applications. So, what are op amps? What are operational amplifiers? We have already seen the introduction of operational amplifiers. Then we have seen the block diagram of op amp. You might be remembering this all, but we will just have a recap of this, and then we will start with the subtractor. So what are operational amplifiers, how they are different from general amplifiers and electronic circuits? All these things we have already seen. Okay, and then we have also seen what are the parameters of operational amplifiers, and we have started then applications of operational amplifiers, that is op amp. So what are different applications of op amps? We have started with op amp as an inverting amplifier. Okay, so this is a configuration which is most probably used with the op amps, that is a inverting amplifier. So what is the special feature about this amplifier is that whatever input you are going to give to this amplifier, it will give a 180 degrees phase shift to your input signal, and at the output you will get a inverted signal. Okay, so this is how the inverting amplifier work. We have already seen the diagram of this, the circuit diagram of inverting amplifier we have already seen, but one more time we are going to see this, because this is required for whenever we are using op amp as a subtractor. Okay, so this is how we use operational amplifier as an inverting amplifier. In this design you can see that the input is applied at the inverting end, and it is given through a input resistance, that is R1, and at the feedback we have connected R2, which is also called as a feedback resistor. Okay, so this signal at the output is fed back to the input, and you will get what at the output is an inverted input signal and with the amplified one. So this is how the input and output look for a inverting amplifier. So these things are very clear to you. Now we have also seen the derivation, the formula for what we use inverting amplifier. So the gain of an inverting amplifier is denoted as minus of RF by R1. This is the gain of an amplifier, and output voltage can be gain multiplied with the input. So how we will have the output is in inverting amplifier is you will have output as gain into V in. Whatever input we are having multiplied with the gain, you will have the output. Now the second configuration of op amp is non-inverting amplifier. We are seeing inverting and non-inverting once again, because we can design an adder by using an inverting amplifier also, and by using a non-inverting amplifier also. Okay, these two configurations we will use to design the adder or the subtractor. Okay, so you can have a op amp as an subtractor by using non-inverting amplifier or by using an inverting amplifier. Only the output voltages will be different. So this is how we have derived the formula for non-inverting amplifier, that is also defined as gain multiplied with the input. So what we have at the input is multiplied with the gain. Ayush Katre, are you there? Okay, so this is the diagram, or this is the circuit diagram for a non-inverting amplifier. Here we have connected the signal at the non-inverting end. That's why it is a non-inverting amplifier. And at the output, we have connected a feedback resistor which is feeding back the signal to input at the inverting end. So this is how the design of non-inverting amplifier. The signals will look like this. It is without any phase shift. That 0 degree phase shift is there in non-inverting amplifiers. Now, after seeing these two configurations, we have designed adder. What is an adder? What is an adder? When you add two things, you will have a addition. So in adders designing circuit also, we'll add two signals to have a final added output at the end. So what is the adder circuitry? It can be with inverting and with non-inverting amplifier. So you can call two types of adder, that is inverting adder and non-inverting adder. We'll see the designing of this. This is what the adder look likes. We have three inputs, v in 1, v in 2 and v in 3. Okay, we have given it to the inverting end, that's why it is a inverting adder. Okay, so with these three resistors we have given the signal to the inverting input, and at the output we have connected a feedback resistor also, which is feeding back the output to the inputs, and we have grounded the non-inverting end. Okay, so this is how the construction of adder looks like. These are the three different currents flowing from three ends or from three different inputs, that is I1, I2 and I3. So what is the final current? It will be IB2 at this end and IF, that is feedback current, at this end. And what we have two terminals also, that is terminal A and terminal B. So IB1 is the current at terminal B. So what we will do to have a adder is we will apply KCL, that is Kirchhoff's voltage law, at the point A. So what we will have, we will apply KCL, that is Kirchhoff's current law, because we are having the currents at three different currents we are having at the at the node. So we are going to apply KCL, that is Kirchhoff's current law. I1, I2, I3 is equal to IB2 plus IF, that is the feedback resistance. This is the feedback current, and this IB2 is the current at node B. So the summation of all the currents will give you the final current at point A. After putting the values, we will have I1, I2, I3 is equal to IF. We will put values of I1, I2 and I3. These derivations we have seen in our last lecture. I'm just repeating because we'll have to see the subtractor. So this is how the addition is there. What is the final equation we are going to see here? That the final equation V out is equal to minus of V1 plus V2 plus V3 in bracket. Okay, so this is how we got this equation, by putting the values of I1, I2 and I3 in above equation. We'll get this value. And if we'll have RF as RF, and see here, what is the condition? Here the condition is, if we'll have RF is equal to R in 1, this condition. Okay, if we'll have RF is equal to, if all the three resistors or all the four resistors, they are of same value, what we will have at the output? We will have minus of. Why this minus is there? Because this is nothing but a inverting adder. So by the formula we'll got a minus sign over here, and at the output we'll have a 180 degrees phase shift of the input signal. Okay, so this is how the addition is done in inverting amplifier. Now we'll see how the non-inverting amplifier adder works. So in non-inverting adder, what is the difference? Here we are going to see in the circuit diagram. Here we have applied the two different voltages, which is to be added at the non-inverting end. Okay, that's why it is called as a non-inverting adder. And at the inverting end, the circuit is same, the feedback resistor is there, input resistor is there, and at the output we are going to measure the voltage V out. So what is the formula for this? The same formula what we have used, just put the values of I1, I2, I3. Note I3 is not there, put the values of I1, I2 and IF over here in this equation. So you will get a addition of two voltages V1 and V2. Now we'll come to our main topic, that is op amp as the subtractor. How we are going to have a subtractor? By using a operational amplifier. This is the designing. You just look at the circuit diagram properly. I'll just wish you all the best that after the Diwali vacations we are expecting our colleges to be opened, so we will be able to perform these things in our practical lab. So whenever you are going to do these things practically, you are going to know actually what happens with the operational amplifiers, and how the addition, how the subtraction is done, how the inverting amplifier works, and how the non-inverting amplifier works. These are very interesting things. So for by the time you just remember this circuit, that this is a op amp as a subtractor, this difference amplifier it is also called as a difference amplifier, because we'll have to take the difference of two signals when we are subtracting the things, or we are subtracting the voltages. Okay, so V2 and V1 are the two different voltages which we are expected to be have a difference of them. So how we have connected? Here one voltage is connected to this end through a feedback resistor, it is connected to V2, and at the V1 we are having a voltage divider. Okay, so here we are going to measure two different currents, and then then the difference at the output voltage. So how this circuit will work? What we are having these circuits as the difference amplifier and subtractor circuits are used to obtain the subtraction of two input voltages. Now these inputs can be anything. These can be positive voltage, this can be a negative voltage, or it can be a negative, it can be a positive. You can take a group of this. Okay, whenever we are doing practicals, so these things will be very clear to you. Okay, how will we are going to have the differences. So here output voltages, we are expecting to have V out as gain multiplied with VA, voltage at point A. Now what is VO1? This will be written as 1 plus, because it is a inverting amplifier. So we'll take 1 plus RF by R1 into RF plus R1 multiplied with V1. So what we will have, we'll arrange this equation, and what we'll have the output is equal to RF by R1 into V1. This is V out 1. Now, what is the V out? That is the output voltage. Here we will have RF by R1. This is the gain of the amplifier, and at the output we will have V1 minus V2. This is how we will have the subtraction of two voltages. Now, here we have written V1 minus V2, but you can have a negative V1, you can have a negative V2. So what we are going to do there, the addition will be there. Okay, so please try to understand the things. These are very interesting things in operational amplifiers. And the first voltage, output voltage, the equation for output voltage is very clear to us, that V1 minus V2 will get at the output voltage. And if we'll have RF is equal to R1, that is if the resistance values of all the connected resistors are same, then what we will have at the output, V out will be equal to V1 minus V2. So this is how the subtraction is done, and this is the final circuit for the op amp as a subtractor. Is it clear to you? Here we are having two nodes, nodes A and node B. So we can have the output voltage of the difference amplifier will be given as RF by R1 into V1 minus V2. If we'll have R1 is equal to RF, we'll have V out is equal to V1 minus V2. So this is how the subtraction is done, and this is the final circuit of your op amp as a subtractor. You can change the values of resistors. If you not put RF is equal to R, or if these resistors are different, you will have a different output voltage. Each and every time you will have to calculate the output voltage by keeping the values of RF and R. Okay, so this is how the op amp as a subtractor works, and I wish you all the best that soon we will having our lab practicals. So this is all for today's class. If you have any questions, you can put them in the chat box, or you can WhatsApp me. Okay.